here, I guess it's pretty nice because you can point it out. Here is crap, and so then once you do use a grid data function, and then you plot the log of the magnitude, that omega 1 and omega 2. And then you get a nice little picture that you see it's definitely the frequency domain. But like outside of this, it's a bunch of n ends outside the circle. Because you have a bunch of projections, so you can't get outside the circle. So if this is 465. Yeah. So out here it's all black and white. Yeah. The thing is so what do you take inside here to reconstruct the image? Because it's a circle. A little different. I just took whatever the biggest square is.
Oh, I see.
That's what and it looks like that. So does that it has all four options. Oh, it's okay. Yeah. Okay, so that's what
Okay, let me get started. What happened to the population of our class? I guess they died. Okay.
Watching videos.
That's right. That's right.
In their rooms.
That's right. So, just a couple of announcements before I get started. Homework number right. Homework number 3 on tomography is due on Friday, and I'll be assigning a new homework on Friday, which is the 17th, which will be due on the 24th. Just to get a quick show of hand, how many people have finished the lab assignment? Or you have? Very good. And how long did it take you roughly?
Oh, a lot of. I probably spent like 5 hours doing the wrong thing, and then I went to office hours and figured out I was just. You gotta just. It's a lot of tricks with the FFT and like how MATLAB does system names and stuff. Looks really good if you use a lot of samples.
Oh, really?
Yeah, you can almost get it back perfect. Well, not perfect, but like really good.
Mm.
I mean, a lot of samples. How many is a lot?
Yeah, well, you have to like pad the original samples to make it. If you do a lot of samples, okay. Certain like pieces make it a little bit tighter, more than 460 or something. Yeah,
Right.
like 1024 or 2048.
My computer won't run that.
Okay, let's see. Um, okay, so what I'm going to talk about today. So overall, how many hours did it take you?
I'd say.
Without the 5 hours that you were in the wrong path.
Oh, once I knew. Oh, well, that was part of it though. I was learning.
Okay, the whole thing,
I'd say
including that.
8 hours maybe.
Oh, that's nothing. That's excellent. Okay.
That's a lot of time.
Okay. Go see Cindy. You have
Hey,
office.
Cindy. Thanks to Cindy, yeah.
Right, right. She has office hours Tuesdays and tomorrow, and you can also catch her after class today, if you're available. Okay, so what I'm going to talk about today is a few more words about FFT and how we compute it. Um, then I'll talk a little bit about a recursive method of transposing a matrix because it relates to the row column technique. And then I'll move on to two-dimensional filter design and say a few words about zero-phase filters, linear phase filters, FIR filters. Talk about a couple of well-known FIR filter design techniques and their extensions from 1D to 2D, and then possibly talk about the transformation technique by McClellan on Friday's lecture. And then that kind of wraps off our discussion off of Jay Lin's book. What I plan to do, hopefully by next Wednesday, because we're approaching the end of February, is come up with a sheet. It's not one sheet, but with a handout of possible projects or literature search or topics that you could spend time to do reading in the field, etc. And I'll try to get that out, as I had said, before end of February. So if this Friday is the 17th, next Friday is 24th. Let's say it's by next Friday. I'll try to do that. And then once you receive that sheet, I want to give you 2 to 3 weeks to kind of look at the topics I've proposed and then come up with your own proposal. Again, this project slash term paper you do should not be all encompassing. It's not something that's going to supposed to chew up hundreds of hours of your time or anything like that. I would put some guidelines of roughly how many hours on average I expect you guys to do. I'm going to look at the rest of the semester, map out the remaining labs and homework that's to be done, and it's meant to be for the weeks that you don't have a homework. And on average you're spending 8 or 9 hours to do the homework. It's meant to be that same number of hours a week, no more, no less. Okay. So don't think of it as a gigantic project. And of course, I encourage you very much to team up after I propose the topics. If you want to do a project and you think that by teaming up you can accomplish more and show something more real, that's perfectly fine. But meanwhile, in the back of your own mind, you should also be thinking about what project you might want to be doing. If you're doing something for your thesis that you think relates to image processing, of course, I'm happy to receive that proposal as well. Okay. Any questions or comments before I get started? All right, so what we talked about last time was two methods of computing DFT. One of them was direct method that, as we talked about last time, you just sum up the values in the double summation, and it ends up requiring approximately n to the fourth multiplications, n to the fourth additions for an n by n sequence. Then we talked about row column decomposition. What we realized was that it requires roughly of the order of n squared log 2n. So let me write these numbers down. So computing DFT for an n by n image, if you use the direct method, you get roughly n squared operations. If you use the row column, then you get roughly n squared log 2n operations. Yeah.
Yeah, when we did the direct method, it was very obvious to me how we got that number n to the fourth, but I don't see very obviously how you get n squared log 2n for this other one.
So if you go back, I didn't bring the lecture notes. I could fire up the computer to look at the lecture notes from last time. But basically what we discovered was you had to do n one-dimensional DFTs across the columns, right? And each DFT is n log n, right? And then once you did the columns, then you have to do n more one-dimensional DFTs, each one being n point long. So that's another n log n. So it's the result of those. Okay? Do you follow that? So to do the columns, let me just flash this quickly. Can you bring this thing down? So the first step, you have n columns. Each column is n points long. So n log n, n log n, n log n, and there's n of them, so it's n squared log n. And then once you do that, then, sorry, initially you do rows, or you can do first columns, then rows, or vice versa. And then you have to do, to begin with, you do n rows. Each one is n points long, so n times n log n. And then once you do the rows, you do n columns, and that's the other one. So you add them up, you get n squared log n operations. Is that more clear?
Yeah.
Okay. So just so that you have a feeling of what these numbers are all about, for example, suppose that you have n approximately 1,000. So you're dealing with a 1,000 by 1,000 image. The direct method then would require approximately 10 to the 8 operations. And if you're doing row column decomposition, you would require 10 to the 4. Sorry. This is 10 to the 3. This is 10 to the 12. Right? And here 10 to the 3 times 10 to the 6 times log base 2 of 1,000 is 10. So approximately 10 to the 7. So comparing these, you get 10 to the 12 over 10 to the 7, which is approximately 10 to the 5. So for 1,000 by 1,000 point image, the saving factor is 100,000 times. So if one of them could take 1 second, the other one would take, let's see, 100,000 seconds is roughly divide that by 60. So 100,000 seconds, divide that by 60 to get minutes. Let's just say that's 120. So you get 2,000 minutes. Divided another by 60 to get hours. So this divided by this is 30. So you get 30 hours. So what that means is that if the row column decomposition takes 1 second, the other one takes 1¼ days, which is a big saving. You don't want to. I mean, if you're, let's say, if it's a one-shot thing, you can wait a day and a quarter to compute the answer. But if it's an iterative algorithm that you keep refining something, is part of your tomography homework said the iterative algorithm? Are they doing the iterative stuff?
Well, no, we just do nearest neighbor.
Oh, okay. Okay. Anyway, so if you're doing iterative techniques where you have to recompute DFT, if each iteration takes a day and a quarter, you're in deep trouble. Okay. So furthermore, if you're doing video and you're supposed to do 30 frames per second, if each frame of yours takes a day and a quarter, you'll never get done. It'll never be practical. Anyway, so there's a big difference between direct and row column decomposition. One thing that I didn't really mention when I was doing row column decomposition, and I will mention it now, is this, in that if you're doing row column decomposition, right? The best is to show this picture, really. There's a matrix transposition step in the middle that we never talked about. And so what do I mean by that? Well, let's look at the pictures. You start with your image like this. Remember that when you're dealing with storage on a computer, the computer doesn't store things in a two-dimensional array. I mean, you specify a two-dimensional array, but on the disk, it stores things, let's say, row by row. Okay? So the way physically how the numbers are stored on a disk is this row followed by this row followed by this row followed by this row. So when you want to do the operation, so you take you read a row, you take a one-dimensional DFT of it, and then you write it into a different matrix. You read the second row, you take a one-dimensional DFT of it, and you concatenate. That's conceptually that's the second row of your picture of this f of k1 and n2, but you concatenate that with this one. But after you've stored these things, so now you've stored f of k 1 comma n2 in a row by row fashion. This row followed by this row, followed by this row, followed by this row, followed by that row, right? And the next step is to do now column by column the FTs. You want to take this column, this column, this column, this column. Now, these points, okay, are not contiguous anymore. They're in fact endpoints, this point and this point on a linear disk, they're endpoints apart. This point and this point are endpoints apart. Okay? So, in some sense, to be able to do the so there's some I/O overhead involved in terms of collecting these data points together, making a one-dimensional array out of it, and taking a one-dimensional DFT. And then after you take the one-dimensional DFT, now I store my data in this manner. It's column followed by this column followed by this column. So in my disk, it's this followed by this followed by this followed by this followed by this, and this is the transpose of what I started off with. In other words, I assume my data was row by row to begin with, and I ended up my final two-dimensional DFT being in a column by column fashion. It's all an artifact of the fact that the disk in a computer is a one-dimensional entity, and it's not a two-dimensional matrix. So essentially, the data has been transposed from being in a row by row manner to a column by column manner. Is everybody clear on that? And at the end of the day, you need to do a matrix transposition. And one way of doing the matrix transposition is Oakland's algorithm, which I'll talk about. It's a recursive method of doing a matrix transpose. Okay, so let me just briefly talk about that. Where's my main sheet? Okay, here we go. So one concept, or can you rotate, please? Thank you. Okay, so the basic thing that I just talked about is that row column decomposition requires a matrix transpose. Okay, so in other words, and the question is, if you do this matrix transport the usual way, you might end up having too many IOs. So the question is, how do we do the matrix transpose in an IO efficient way? That's kind of the key question you want to ask yourself. And the answer is, there's a technique called Oakland's algorithm for transposition. And this is a recursive algorithm. And if you start, I'll show you how it works in just 1 second, but basically, if you start with an n by n matrix, then you need log 2n stages, as you would imagine, for the thing to get completed. And the basic idea behind, so basically Euclid's algorithm is a fast, non-IO intensive way of doing matrix transpose. Okay. And the reason it's a log2n, it has log2n stages and it's a recursive algorithm, is the basic idea behind it is divide and conquer, similar to FFT. And it is basically based on the following observation, if you can roll up just a little bit. So the key observation you need to make is the following. If I have a matrix A, which I can divide it into 4 submatrices, A1, 2, A11, A12, A21, A22, and it doesn't matter how big A is. A could be 1,000 by 1,000, in which case each of these are 500 by 500. Okay, so let's say A is n by n. Then A transpose is transpose of each of these pieces, A11 transpose, A22 transpose, but not A12 transpose. Here, you first switch the place of these two guys before you transpose them. So it would be A21 transpose, A12 transpose. Okay? And the easiest way of seeing that in a simple example kind of way is, suppose A is a 2 by 2 matrix, x11, x12, x21, x22. Then the transpose of it, we all know, is x11, x22, x21, x12. So that's a 2 by 2 example. But you can also convince yourself with more like a 4 by 4 or 8 by 8 or larger size picture. So I'm going to now resort to the nice pictures in Eennlb's book. So I don't have to do to draw these pictures myself, because it takes a long time and it will never be as nice as this. So if you can zoom in, great. So suppose that I have a sequence like this, or a matrix like this, and I want to. Can you focus it, please, so people can read the letters a little bit better? Because no. Okay, great. Thank you. So these are the elements of my matrix, or whatever the thing is I want to transpose, and it's x11, x12, x13, all the way to x18 here, and x21, 22, 23, 31, 41, etc. So, and so given that matrix identity that we just wrote down, that transpose of A is transpose of each piece, except that the diagonals are swapped. What does this tell you? What our approach is that we've started with a problem that was n by n, and we've decomposed it into 4 problems. Each one is n over 2 by n over 2, plus a little overhead. And what's that little overhead? Well, in this picture, the little overhead is the fact that this is A21 and this is A12. I had to swap the place of these two things. So if this was A12 transpose and A21 transpose, then I've just perfectly divided an n by n problem into 4 n over 2 by n over 2 problems, and I'm done. I just keep doing it and finished. But there's a little bit of overhead, and that is the overhead comes from the fact that these two guys had to get swapped. And it's the swapping of these two guys that causes the whole algorithm to have non-zero amount of work involved in it. So in each step, you can imagine, in each step what I'm going to do is I'll start with this, and then I swap these two guys with each other, and now I've decomposed my problem into 4 n over 2 by n over 2. And then I go to each one of these little guys, and I repeat the same thing. I swap the diagonal of them. I swap the diagonal of this guy, swap the diagonal of this guy, swap the diagonal of this guy, and I keep doing that until I'm done. Is everybody clear what the basic idea is? Yeah? So the question is, that swapping that we do, how much does that cost us? Kind of like FFT. FFT, you decompose an n-point problem into 2 n over 2 point problems, plus a little bit of overhead. It's that overhead that causes FFT to have non-zero amount of operations. It's the multiplication by the total factors, etc. And here, it's the swapping of A12 with A21 that's the overhead that we have to keep track of, that causes the whole matrix transpose to have non-zero number of operations. Is that clear? Okay. So coming back here now, if you can zoom in one more time, great. So how much? So staring at this picture here. So this is the first stage. All we have to do is move this blah into this blah, and this blah into this blah, in order to get something that looks more like this. Can you zoom out just a tiny bit? Thank you. So in essence, this square of numbers, this array of numbers here, as a whole, imagine being transposed, moved from upper left to the lower right. x81, x82, x83, x84, have been written here. x81, x82, x83, x84. This row is here, this row is here, and this row is here. And furthermore, this square has moved up here. So now you got x45464748, x45464748. Okay? So the first step involves that, and then the next step, now we have to swap this 2 by 2 by this 2 by 2, this one with this one, this one with this one, and this one with this one to get this new thing. And now that you have 2 by 2 matrices, we just transpose each one and we're done. Okay?
The direction they swapped was different from what you wrote down.
Yeah, because he's
What's the?
this is still what I wrote down here is true.
So it doesn't matter.
Well, this thing here in this picture is primarily for illustration purposes. This relationship is still very much true, which is if A is in this case, these are the two things that get swapped. He's just chosen his matrix elements to be diagonal the other way. It's just a notation he screwed up in the book. Right. It goes. Yeah. He shouldn't have done that. I knew that question would come up, but okay. The way he's indexed things is slightly off. But the basic idea is the same. You swap these two things, then you have smaller matrices, you swap these things, and then you come into 2 by 2 matrices and swap, and you're done. So you can easily see that if you have an n by n image or n by n matrix and you want to transpose it, how many do we all believe? How many stages can we all intuitively see how many stages there is in this transpose? If this is n and this is by n, you know, we started by 8 by 8, and we have stage number 1, stage number 2, and stage number 3. So you can easily see that it's log base 2n stages that's needed until we get to matrices that are small enough they're just 2 by 2. And furthermore, at each stage, the number of IOs is fixed. Let's just, for the sake of convenience, compute the number of IOs that we need to transpose to move this square here and this square here real quickly. How many IOs do I need? Well, I need 1 IO to read this entire row. I realize I only need to read half the elements, but whenever you do a disk IO, as I'm sure you know, you always end up reading more numbers. Even if I want to read like 4 numbers, I end up having, there's a minimum number of elements in the array that the read returns to me. I don't care about the remaining numbers because I'm not going to touch them, but nevertheless, I get those anyway. That's for free, essentially. But let's not get sidetracked with such details. Anyway, I read this, and I read this row, and I swap them. Let's say I put this row in memory, and I put this row in memory. Then I write the row I write this row. I write the first 4 elements of this row here, and I write the first 4 elements of this row that I stored here. Did everybody follow me? So there's a total of 2 reads and 2 writes. That's all I'm trying to get at. Read this row, read this entire row, store them somewhere, let's say in cache or something, and then write back the 4 elements of this row up here, and write back the 4 elements of this element of this row back here. So there's 4 IOs that's needed per row. Okay, and how many rows do I have to do this over? 1, 2, 3, 4. In other words, n over 2. So 4 IO per row, and n over 2 rows. 4 times n over 2, it's 2n IOs. And you can convince yourself by looking at this diagram that the number of IOs in every stage is also still continues to be 2n. Okay, so having seen that, let me come back here and write some of these things down. So let me come back here. So it's an iterative kind of a algorithm, and as I said, there's so the number of stages of decomposition, I call this decomposition, is log base 2 of n stages. And in each stage, we end up doing 2n IO operations. As an example, let's just look at the first stage. If I look at the first stage, I have to do 4 IOs per row, and I have n over 2 rows. So multiply these two things together, I get 4 times n over 2, which is about 2n IOs. Okay, and I realize I'm writing too small now. You might not be able to read, so let me make this bigger. So it's 2n IOs per stage. So if I have 2n IO per stage and I have log 2n stages, I can put these things together and write down that the total IO count is then 2n log 2n stages. Okay? And so, so this is how much Eennlb's algorithm requires for matrix transposition. Okay. So how is this used in the row column decomposition? Well, again, you start with your data. You do row DFTs, and okay, and then you do a transpose, and then you do column DFTs, and then followed by another transpose to get the data back into the right. So you do the transposition essentially twice. Yeah.
Yeah, so you were talking about 2n IOs per stage.
Yeah.
But it seems like as you go to the second stage, you're only going to have, you're going to have to do the 2 reads and the 2 writes, but there's now going to be n over 4 rows instead of n over 2 rows.
Let's go back to, shall I bring the book?
Actually, you know what? No, because there's going to be more squares though, so it's...
Right. So is everybody clear about this whole argument? Okay, so essentially, and you might say, okay, so this one is going to take 2n log 2n IOs. This one is going to get 2n log 2n IOs. And you might say, well, how about the IOs needed for row DFT and column DFT? Well, those are minor compared to 2n log n. Each time you read, let's just go over that. So each time I want to do a one-dimensional DFT of a row, I do a read, one read, and then I do one write, right? And I have n of these guys, so I have to do n reads and n writes, right? So this stage really requires 2n IO, and the same thing here. After I did the transposition, I did 2n IO. But so as so the dominant thing here, because it's so the total IO, if I were to count it, would be 4n plus 4n log 2n, and many times this is going to be much bigger than that, so I can be approximated as just 4n log 2n. This is the IO need for the row column decomposition. Okay. So I'm going to just write down C figure 3.20 and 3.21 of Eennlb for the details of this Eennlb's algorithm, because I didn't want to write down all the matrices and the numbers and the rest of it. By the way, Eennlb is a Scandinavian name. Do we have a Scandinavian person in our class? We did last time, by the way. But he corrected my pronunciation. That was 3 years ago. I already forgot what the exact. He said Eennlb or I can't remember now. We have a Swiss guy. Actually, Sam is not here, but he could have corrected all of our German and French mistakes, but he's not here today. So Okay. Any questions or comments on this? So in general, in signal processing, there's a lot, this notion of divide and conquer and doing recursive algorithms to start with something big and then to divide a problem of size n into a problem of two n over 2's and then keep recursing on it. It happens all the time. And I think in our undergraduate curriculum, Alan Gu probably can attest to this better than I can. We have CS170, an algorithm course that do they talk about recursive algorithms, divide and conquer, and they talk about FFT as well, right? They ran out of time. Oh boy, okay. Huge mistake. Graph algorithms. How about sorting and stuff like that? They don't cover sorting either. Some other class. Okay. Okay. All right. But we have a great deal of respect into signal processing for FFT because it's really what revived the field in 1963. Before that, people couldn't compute discrete Fourier transform fast enough. Again, because of this factor that I just talked about, the 10 to the 5 here, if you do direct method, you end up chewing too much time, especially with those computers that existed then. And again, of course, you could argue computers are so fast today. Why do you care about speed reduction? Well, the answer is yeah, the computers are fast, but how about your cell phone? Do you want your hands to melt as your phone is computing FFT of images that it received or whatever it's trying to do? So, so low power, low complexity is always of importance. Next, I'm going to quickly move on to the third method of doing FFTs. So we've so far talked about direct and row column, and now I want to talk about the vector radix FFT. And as I mentioned last time, this vector radix FFT is kind of the true translation of divide and conquer in 2D. Okay, and it does result in lower operation count than row column decomposition, but at the end, it also results in a computer program that's a lot harder to write, a lot more complicated, a lot more intricacies than using row column decomposition. So in practice, I bet you, for example, the 2D FFT, the algorithm you're using in your MATLAB, I'm almost sure does row column decomposition and not vector radix. But let me just explain the basic idea behind it anyway. So before doing that, I want to just recall the 1D case just for completeness. So you start with the sequence x of n. Now you divide it into even points and odd points. And just as a reminder for you, when you do one-dimensional DFT, one-dimensional FFT, there's decimation in time and there's decimation in frequency. But for now, I'm just talking about decimation in time, right? So divided into even points and odd points. I call this sequence x sub e of n. I call this sequence x of o of n. And then I plug in. So this is an n over 2 point sequence. And this is an n over 2 point sequence. And x of n is an n point sequence. So I compute these two things. And then I get the output of these guys. And I'll just show the top input, the first output and the first of this box and the first output of the other box, and you do a butterfly type operation. Okay, first of all, you multiply this bottom one by twiddle factor WNK, where WNK is e to the minus j 2 pi k over n. Okay, that's the definition of it. So this is called the twiddle factor. You multiply this number by a twiddle factor, and then you shove it into a butterfly. That means this number gets added with this number here to result in this output. And then this number gets subtracted from this number to result in this other output. And this could be the kth output and k plus n over second output. So I get the kth output And this one is the kth output itself. So this guy has n over 2 outputs. I get the kth one, multiply that by w and k, add to get the kth answer of the final answer, and then subtract in the butterfly to get the k plus n over 2 answer. And I keep doing that for k from 0 all the way to n over 2, and the last one that I get is nth answer. Okay? So is this picture familiar to most of you? Not to you. Okay. Watch the 123 1 hour. There's only one lecture in EE 123 that talks about all the details of FFT, and I think it's pretty entertaining. Pretty entertaining lecture. If nothing else, it allows you to get a good night's sleep. You fall asleep in front of it, and it allows you. No, just joking. So is everybody? I guess other than Chris, is everybody familiar with this picture, or are there more people who necessarily don't know this? Just to give me an idea of how much detail I should provide right now. I need honest feedback.
I've seen it in the past.
I might have seen a picture in the document.
Okay. So let me do the 2D version, and maybe that would become a little bit more clear, because that way with one bird we kill two stones. For people who haven't seen the 2D will understand it, and then I think the 2D itself can explain how the divide and conquer idea works. Okay. So here the vector. So in 2 dimension you have a sequence g of n1 and n2, and I'll just show it for a very small case, n1 and n2, and suppose this is a 4x4 sequence. Okay, and I'm going to divide this into 4 sequences. Okay, so divide G into 4 subsequences. Let's call it subsequences. Okay, and G itself is 4x4, and the subsequences are GEE of n1 comma n2, GEO of n1 comma n2, GOE of n1 comma n2, and GOO of n1 comma n2. So E stands for even and O stands for odd. Okay, and I'm going to show each of these sequences with a different symbol here. So GE, so E in the first index means that it's even for n1, even for n2. This one, even for n1, odd for n2. So GEE sequence is going to have even indices for n1 and even indices for n2. So if this is 0, 1, 2, 3, 0, 1, 2, 3, so this is around GEE. Okay, so GEE is this, even index in n1 and in n2. And then GEO is even in n2, sorry, even in n1, odd in n2. Okay, so I'm going to use this upside down triangle to show that. So that'll be this one. So it's even in n1, so 0, this one, and this one, and it's odd in n2. So GEO is this guy. So even in n1, odd in n2. And then GOE, I'm going to put right side up triangle, which is odd in n1, even in n2. So it'll be this guy, this guy, this guy, and this guy. And finally GOO, which is I'm going to use this one, which is odd in n1 and odd in n2. So it'll be this guy, this guy, this guy, and this guy. So similar idea. I started off with an n by n problem, and I've now decomposed it into 4 n over 2 by n over 2 problems. So the question is, how is the DFT of G related to the DFT of these other guys? Okay, so if you can roll up just a little bit. So the question is, how is the DFT? Remember, at the end of the day, FFT is just a method to compute DFT, right? So how is the DFT of G related to DFT of GEO, GEE, GOE, and GOO? These are become pretty tedious to talk. Geo, Joey, Goo, and G. Jesus. I've only used these names this time I taught the course. So again, let me resort to the book because it's got plenty of good pictures that if I were to attempt to draw it on here, it would take me much longer. So I'm going to show, let me even write down what I'm going to show. So show figures 323, 324, 325 of Eennlb's book. And fantastic. Okay. Okay, so this is 323. So if you can zoom in as, okay, great. And are we in focus? Yeah, mostly. So this is, oh, he's using X instead of G. So let's not worry. The name of the sequence doesn't really matter. So it's again a 4x4 sequence. And then he subdivides it. So it's x of 0, 0, x of 1, 0, 2, 0, 3, 0, etc. And then he subdivides it into these 4 subsequences. So this is GEE, GOE, GOO, and GEO. Okay? Each one of these is now a 2x2 sequence, right? So we started with a 4x4 sequence and we divided it into 4 2x2 sequence. In general, you start with an n by n sequence and you divide it into 4 n over 2 by n over 2. When you were in one dimension, you start with an n point sequence and you divide it into 2 n over 2 point sequences. But here, 4 n over 2 by n over 2 point sequences. And the idea now is that I take the DFT of this guy, the 2 by 2 point DFT of this, 2 by 2 point DFT of this, of this, and I now get this picture. This is a 2x2 DFT of GEO, GOO, GEE, and GOE. And I combine these 4 numbers in order to form the output here, 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 and here. And I combine these 4 numbers that I have a square around them to form this number, this number, this number, this number. And I combine these 4 numbers here to get this point, this point, this point, this point. And I combine these diamond-shaped 4 numbers here to get diamond-shaped points. And the reason I can do that is because, coming back here, because the answer to this question that I posed is as follows, is that if I start, let me just have a consistent notation with the notes I have here. I call this sequence X. So let me just call it X, but X gets decomposed into GOOs and etc. Because the DFT of X is related to the DFT of these 4 subsequences in the following way. X of K1 and K2 is the 4 by 4 point DFT of X is GEE of K1 comma K2, which is a 2x2 DFT of GEE, plus GOEO of K1 comma K2 times e to the minus j 2 pi K2 over n, plus GOE of K1 and K2 times e to the minus j 2 pi K1 over n, because this is odd here, you get K1, because this is odd here, you get K2, plus GOO of K1 and K2. Now I have 2 Twiddle factors, e to the minus j 2 pi K1 over n, e to the minus j 2 pi K2 over n. Okay? Where GEE is the n over 2 by n over 2 point DFT of little GEE. GOE is this of GOE, and then GEO is this of GEO, and capital GOO is n over 2 by n over 2 point DFT of GOO. And so pictorially, what this looks like is as follows. So let's stare at this and draw a conclusion from it. I wanted to do an n over 2, but I wanted to do an n by n DFT of this guy, and I decomposed it into 4 n over 2 by n over 2 DFTs plus a little extra factor. Where is the little extra factor? It's this multiplication, this times that, this times that, this exponentials times that. It's that extra little plus thing that adds up and results in having non-zero total number of computations. If I could just do it without these total factors, boy, I'd be done. I just keep decomposing until I get 1 point DF 1 by 1 or 2 by 2, and boom, finished. But in each stage, I have to do a little extra work, which is these total factors, which results in non-zero computation. So let me pictorially show what this summation looks like. This is figure 325 of limbs. Can you zoom in as much as you can? I want to see the whole picture, though. Out, yeah. In, a little bit more in. Okay, I guess there's finite granularity of how much we can control the camera. So here we go. Pardon? That's right, it's quantized. Actually, it's not quantized to predefined levels. It's the delta that you can move it. That's coarse. Okay. Oh, now we challenged our operator. Okay, that's excellent. Can you guys read these letters? Yeah. Okay. So this is GEE. This is the 4-point sequence. This is GOE. This is GEO, and this is GOO. Each one are 4-point sequences. I shove them into a 2 by 2 point DFT box. And now this is capital GEE, capital GOE, capital GEO, and capital GOO. These are the DFTs of these input sequences. And this box here shows that summation that I wrote down with the exponentials in a nice way. So the output of GEE, you don't multiply by anything. The output of GOE, you multiply by a twiddle factor, which is e to the minus j 2 pi k1 over n1. This is e to the minus j 2 pi k2 over n2. And again, J-lim is assuming the sequence is n1 by n2 point. We're assuming it's n by n. That doesn't matter. And the output of GOO has 2 twiddle factors, wn1 k1, wn2 k2. And then you go into what's called a butterfly, okay, to compute this output, this point, this point, this point, this point. This is a butterfly with 4 inputs and 4 outputs, okay? So in general, every butterfly has 4 inputs and 4 outputs. So if I was doing a, I don't know, 32 by 32 sequence, then each one of GEOs, these G guys, would have been 16 by 16. So I'd have 16 butterflies, right? Each with 4 input, and oh, that didn't make any sense. If I had 32 by 32 sequence X, each one of these guys would be 16 by 16. Okay, so it'll have 256 outputs. Okay, that makes sense now. So then I'll have 256 butterflies, each with 4 input and 4 output, and that would comprise my entire, that would span all my output points. Is that clear? What I'm trying to say is that there's a little bit of a problem with giving a 4 by 4 example, because you don't really know whether the size of the butterfly is 4 by 4. Is it because the sequence was 16 by 16 or not? The answer is no. The butterflies always have 4 inputs and 4 outputs, and they're always of this kind of a structure. Is this point clear? So this is exact translation of this summation that we wrote here, except that they're using the notation wn1 k1 versus exponential. So this butterfly gives us 4 output points, and then another butterfly would combine this point, this point, this point, and this point, and it gives you x00, x20, x02, and x22. Another butterfly would combine this point, the third point, third one, third one, third one, and third one, and it gives us the third point, this one, this one, this one, and this one. Finally, the fourth butterfly will combine this point, this point, this point, that point to get this, 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 and that. So that's kind of the story behind it. So staring at this thing once again, how many stages are there? And how much work do we do in each stage? All right? So how many stages is it? Well, if you have an n by n image, first you go into 4 n over 2 by n over 2, and then each one of the n over 2 by n over 2 becomes 4 n over 4 by n over 4, and each one of n over 4s by n over 4s becomes 4 n over 8 by n over 8s, and on and on and on. So how many stages does that result in? That's it, exactly log 2n. It doesn't matter that it's n by n, it's the same thing. N becomes n over 2, n over 2, n over 4, n over 4, n over 8, etc. So coming back here, if you can bring the camera, thank you. Okay, so great. So start with an n by n, then it becomes 4 n over 2 by n over 2, and then each n over 2 by n over 2 becomes 4 n over 4 by n over 4, and then each of the n over 4 by n over 4 becomes 4 n over 8 by n over 8. So it keeps on going. Therefore, you can easily see that there's number of stages is for an n by n image is just log 2n. Okay, and in each stage, how many butterflies do I have? Well, in general, there's n squared input, n squared output. In each stage has n squared inputs and n squared output, and therefore, and each butterfly has 4 inputs and 4 outputs, and no two butterflies share its inputs and outputs. Therefore, there's n over 2 over 4 butterflies per stage. Okay, so if I look here, let me write down some of the things I said. And also, each butterfly has 4 inputs and 4 outputs. And furthermore, they don't share inputs and outputs. That's why you get n over 4 butterflies per stage. And you can easily convince yourself with that by staring at this one more time, is that there's 16 inputs, and I'm showing one butterfly. You could have 2, 3, 4. So 16 over 4, so 4 butterflies. And once you've done that, then you can decompose each of these things further until you get done. So so combining these two ideas together, the fact that we have log 2n stage, can you roll up just a little bit? So we have log 2n stage, and we have so many butterflies per stage. So the next question becomes is, how much computation per butterfly do we need? Okay, well, that's a good question. If I look at the way, again, if I look at pictorially what this summation, this decomposition here, this shows me the compositions of the n over 2 by n over 2 DFTs into making the x, into making the n by n DFT. I translate that pictorially into this. This is a structure of a butterfly. It has 4 inputs. In general, the K1 and the K2 point of GEE GOE, GEO, and GOO get combined to result in x of K1, K2, x of K1 plus N1, N over 2 at K2, x of K1, comma K2 plus N over 2, and x of K1 plus N over 2, and K2 plus N over 2, right? So this is the structure of my butterfly. It's got 4 inputs and 4 outputs. And what's the number of operations that's needed? How many multiplies do I need in this butterfly? Anybody? Right, just 3. This one, and that one. I don't count multiplication by -1 because it's not, you don't have to multiply by -1. This just means that there's a subtraction going on. So we need 3 mults, and how many adds? Adds means adds or subtracts do we need to compute this butterfly? For each output point, there's 4 arrows coming in. It's a addition of 4 numbers. So how many adds do you need to add up 4 numbers? 3, right? So 3 for this guy, 3 for this guy, 3 for this guy, and 3 for this guy. 3 times 4, 12 adds. So looking at this butterfly picture, we need 12 adds and 3 mults. Okay, can you roll up? Can you zoom back, please? Thank you. Okay, so now I'm going to put all of these things together. I have log 2n stages. I have n over 2 butterflies per stage. And I have 12 adds and 6 multiplies per butterfly. So multiplying all of these things together, I get the number of adds then is n over 2 over 4 times log 2n times 12. And the number of mults would be n over 2 over 4 times log 2n times 3. Okay? And in a second, I'm going to show you another. So approximately speaking, this becomes 3n squared log 2n, and this becomes 3/4 n squared log 2n. Okay? And there's one more trick one can play in 2D that you can't play in 1D, and that is we can simplify the structure of the butterfly. So the number of adds and the butterfly, the simple way of doing it is 12 adds, but it can be reduced from 12 to 8. Can go from 12 to 8. And let me explain to you how that works. It's a pretty simple thing, and it takes very little time to explain. So, so here's my GOEs and GEOs, my n over 2 by n over 2 DFTs. Okay, and it's coming into this box to result in x of k1 and k2, and then x of k1 plus n over 2 comma k2, and then x of k1 comma k2 plus n over 2, and then x of k1 plus n over 2 comma k2 plus n over 2. Okay, so and then the twiddle factor is here, wn1 k1, and I'm basically repeating Eennlb's picture, wn k2, wn k1 plus k2. So now it's I have to do this, and then this. I think we did all of them, right? Oh, there's one missing. This one is missing too. Okay, so that's our 4x4 butterfly. I finally had to draw what was in Eennlb's book. But Here is the way you reduce 12 to 8. Let me relabel some of these things. I'm going to call this point, the value at this point, A, B, C, and D. Okay? And if I do that, then I'm going to define new intermediate variables. In particular, capital A is A plus B, capital B is A minus B, capital C is C plus D, and capital D is C minus D. Now, if I define these, then I can say that, look, x of k1 and k2 is nothing but A plus C. X of k1 plus n over 2 comma k2 is nothing but B plus D. These are all capitals. X of k1 comma n over 2 plus k2 is nothing but A minus C, and x of k1 plus n over 2 comma k2 plus n over 2 is nothing but B minus D. Okay? So if I define these variables, then I can write my outputs that I need in this way. So I don't need to do, previously the naive way of counting the number of adds was 3, 3, 3, 3. That's 12 adds. How many adds do I have to do under this new approach, the technique? 8. So I can get away with 8 adds. So coming back up here, you can roll up please. Great. So coming back up here, I can further reduce the number of adds from 12 to 8. That means I can do n over 2 over 4 times log 2n times 8, which is 2n squared log 2n. And so that's the number of adds. And the number of malts remains the same, which is 3 over 4 n over 2 log 2n. Okay? Okay. Now that all is said and done, what's the upshot of all these things? So we have the vector radix FFT, which is a true translation of what FFT was about. And then we had the row column decomposition. So what was the operation count for row column decomposition? If you all put it in some sort of a table, so here's number of malts, and number of adds. And here is row column, and here is vector radix. So we just did vector radix, so let's just fill this up. It's 2n squared log n adds, and it's 3/4 n squared log n malts. And the row column decomposition requires n squared log 2n malts and 2n squared log 2n adds. So there's no, so the number of adds is a toss-up, and there's no that big of a difference between the number of multiplications. There is a factor of 25% difference, I agree with that, but that difference doesn't grow as n squared or with the size of the image or even the log of the size of the image. There's no factor like that. So if one method, for example, takes 1 second, the other method takes 3/4 of a second. If one method takes a day, the other method takes 3/4 of a day. One is just 75% of the other one. And you could theoretically argue that actually we have, how many of you are experienced C programmers? Yeah. Would you think which one of the two do you think is easier to program in C? I totally agree. I think implementing the first one is much simpler, and I bet you that if you actually, this bet can never be verified in one way or the other, but I bet you if we dug into the MATLAB implementation, it'll just be using the row column decomposition. But what you do want to avoid is the direct method, because the direct method is just a suicide. It's n to the 4th. So the thing that you want to really remember is avoid these guys, because if you do, then it becomes a matter of 1 second versus 1.5 days or 1.25 days, and you you don't want to get into those kind of trade-offs or those kind of situations. Okay. Any questions or comments? Okay. So I'm gonna talk a little bit about filter design, just preliminary stuff. What what the different kinds of filters are in 2 dimensions, so that the stage is set for when we start talking about uh, um, transformation technique on Friday. So so 2D FIR filter design. FIR stands for finite impulse response. Again, we're dealing with linear time invariant or linear shift invariant systems. They all have impulse responses, and finite impulse response means there's finitely many non-zero values in there. Okay. And we've already talked a lot about the fact that IR filters are hard to derive stability for. We've talked about ways of realizing IR filters using difference equations and how to pick boundary conditions, and so that they're recursively computable and they correspond to a linear time invariant system. All of those nice things. But for the most part, when you're dealing with image processing problems, you'll be dealing with FIR filters. Simply because they're stable and they also result in zero phase, or linear phase, if you will. And linear phase is always important in image processing applications to preserve edges. So there's basically, generically speaking, there's 3 steps for designing FIR filters. Come up with filter specs, and that's very much application dependent. Somebody comes to you and says, look, I want to design a low-pass filter or a high-pass filter, and these are the specs for it. Then there's the design of the filter. You have to decide, what filter you want to use. That means determining the coefficients of h of n, the impulse response. And then the last step is implementation. And the implementation could be lots of different things. You could be implementing it in an ASIC. That could take 2 years to design, tape out, debug, fabricate, all those things. You could be programming a DSP chip, for example, a TI or an analog or whatever. And there's the programming DSP chips is kind of in between programming in assembly and programming in C. It's not as high level as C. It's not as easy as programming in C, but it's not as tedious as assembly. But there's simple instructions like FFT, convolve, simple things like that. How many of you have actually programmed DSP chips? Okay. Actually, what application was it and what chip did you program?
What was the TI evaluation board?
Uh-huh.
For a CD design project.
Oh, okay. And what application did you?
It was it's a acoustic processing.
Gotcha.
So it was a linear prediction algorithm.
Uh-huh. And I guess I'm curious. Last time I looked at them, they had instructions like convolve, FFT, stuff like that. Did they have any other high-level instructions?
Well, there's a TI actually came out with like this programming. So
Right.
they have their own programming environment for that.
Right. But what were famous signal processing operations that they gave you in that programming environment for free, so you didn't have to write it yourself? Like inner product.
Yeah. So yes, there was FFT, the
Mm,
inner product convolution.
that kind of stuff.
So they had also, I think, some simple filter.
Simple. Oh, I see. Okay. And you program TI chip as well?
Yeah, it's the outside evaluation, the C5510.
Uh-huh.
So it's for like a MORAN application.
Which application?
Like a MORAN receiver design.
LORAN.
It's like the precursor to GPS.
Oh, okay. I know what GPS
It's
is.
a senior project as well.
Okay. Okay. And did you find it to be harder than C to program? With DSP?
We did a lot of it in assembly.
So that was more difficult. Yeah. Okay. Okay, so you can program things in DSP chips. And by the way, there's companies, for example, that come up with VSPs, video signal processors. These are chips that are specialized, that have specialized APIs and instructions to do video operations. Like, you give it frame 1, frame 2, compute motion estimation, give me the residue. Or give frame 1, compute the DCT. And examples of those are, again, TI is very big on that. TI is the largest DSP chip manufacturer in the world. And there are more TI chips in cell phones than any other chips. Actually, TI chips, at one point, they were like in 75% of all the chips in the world, all the cell phones in the world. And then there's Equator, for example. That's a video signal processing chip where you program things in there. Okay. So, this is somewhere between, a cross between. It's not as tedious as assembly, although one of us says it is. Hopefully, there's some instructions that make our life easier. DSP special operations. Then you can also do general purpose computing in C, for example, on a PC or on a workstation or whatever. Right? You have an image and you just you open up the Microsoft Visual Basic and program something in C, or if you're in Solaris, you write a C code and compile and give the input image and see what it is. And the beauty of C is that it's high-level programming. You don't have to dig into the assembly level of, okay, this register now gets this value and let's transfer this register to the other one. It's just not so messy. So as we move down here, it's easier to implement, and takes less time to implement. But what do we give up as we move along this direction? What do we give up as we move from ASIC to DSP chips to general purpose computing? Yeah, there's more specific instructions here, but think of the two extreme, A6 versus programming in C. Speed. I can do if I have exactly, if I'm doing something very special and I built an ASIC for that job, it is no longer general purpose anything. That ASIC can only do that job that I designed it for, but it's doing damn fast. It's going to be many gigabits per second throughput, for example, or terabits per second throughput, whereas the general purpose computer is very easy to program. It'll take you 5 minutes to cook up a C program that does linear filtering on the computer. Even though it's got a X gigahertz CPU, it'll never be as fast as if you design a dedicated ASIC to do it. On the other hand, if you change your mind and say, the filter I really wanted to implement wasn't this, it was something else, the ASIC takes another 2 years before you do it, before you come up with the right filter tabs. On the computer, you just change the numbers, in 5 minutes you're done. So there's trade-offs as you move around here. There's ease of programmability as you move down. A DSP chip is much more programmable, easier to program, quicker to come up with a solution than an ASIC, and a C program is even easier to come up with a solution, whip up a solution than a DSP chip. However, these guys are, as you move up, you have less flexibility but more speed. And in fact, your teaching assistant, Cindy, besides asking her homework question, you can ask her about her research. She's implementing an ASIC that does the compression for lossless layout compression for lithography, massless lithography project. And so her thesis is actually a prime example of a situation where she implements the compression algorithms on the computer, and now she has to translate that into ASICs and make all those things work. And on an ASIC, she's shooting to get 500 gigabits per second, something that no computer can process, no matter how fast it is in today's world. And you can ask her how many years it's going to take her to tape it out and fabricate and debug and test. That's essentially a PhD thesis, right? You can get a PhD thesis off doing an ASIC, but you can't get a PhD thesis off for writing a C program that does something. Okay, I think I'm gonna stop here, and next time we'll continue the discussion on FR filters.
First you find the FFT of those FFTs. So you know which column it's in. And then after you get that, you start assembling the filters. And then you do the IFFT.
So Chris, you might want to watch, go to the website for the radon selected, or just next door.
Right.
It
Well,
have to be
the
just-
2D case made it.
Oh,
a
made
lot
it clear?
more-
Oh,
yeah.
okay, very good, very good. I wasn't quite sure whether it was confusing or.
No,
Right.
yeah, it
Okay.
kind of.
All right, very good.
Oh.
Is there from 0 just to 5 here? Oh, okay. Okay. So would you just use the FFT shift to resolve the FFT? No, like you want to this is a space. If you take the FF, well, if you take the rate of transfer of this and take the FFT of the rate, then if you shift it, you shift all the DC to this, the center of the columns, right? Right. You shift each column, right? That's exactly what I did. And then you do the interpolation between each coordinates. You get a power spectrum if you just plot the absolute value, where like the DC is in the middle and it expands out, right? You want to Fourier transform that again, right? So that it goes up. Inverse Fourier. Right, inverse Fourier transform. Right.
So you want to get
to
the
shift
linear.
this again. You want to shift this again
Right.
so that
Yeah.
it goes to the outside. Uh-huh. Oh, I don't understand that. Right. Right. Yeah. It won't show up with the magnitude as well. Ooh. So you want to shift this back to this position here. So you start like when you have the radon, you have all these like R here and then here, right? So then you want to do just the FFTs of each of these columns. And then